Hi everyone, welcome back to Sigma Maths. This is the third A-level sequences and series video, and we will be looking at geometric sequences and series. Let's start by having a look at a typical geometric sequence. We can see that in order to go from one term to the next, we have to multiply by 2. This is how we know that we are working with a geometric sequence. It will have what we call a common ratio. This is the number that you multiply by to go from one term to the next all the way through the sequence, and we denote it with an R. The first term of the sequence, much like we did in arithmetic, will be denoted by an A. If we wrote the sequence out in a more general way, we would start with A, our first term, and then as we are multiplying by R to go from this term to the second term, our second term would be AR, multiplied by R again, AR squared, and it would continue in this way. If we wanted to write down the nth term, which we will call UN, just like we did with arithmetic, then we need to look at the relationship between the terms we have just written down and the values of n, the position. We can see that we always have an A in every term, and that the relationship between the position in the term and the power of R is that we do one less than the position. So we'll have A times R to the n minus 1. So now we have our general nth term of a geometric sequence. We're going to do a couple of questions now using this nth term before we move on to the sum to n terms. Okay, so here we have the second and fifth terms of a geometric sequence are 12 and 768. We need to write down equations using our formula to relate these two numbers back to the unknowns A and R. Our aim of the question is to write down the nth term, so once we've found A and R, we'll basically be there because we can just stick them into the formula. So the second term will be denoted by U2. This will look like A times R to the 1, and it's equal to 12. The fifth term, U5, will be denoted by A times R to the 4, and this is equal to 768. So once again we have simultaneous equations. We met a lot of these in the arithmetic sequences work. However, we are not going to solve these by adding or subtracting like we did with the arithmetic ones. These ones need to be dealt with using division. If I label my equations 1 and 2, then I can see I can eliminate A, as it has the same power in both equations, by dividing, and it will be nicer to divide larger by smaller, so we'll do 2 divided by 1, which will give us AR to the 4 divided by AR equals 768 divided by 12. As planned, the A's cancel, and here we get R to the 4 over R, which is R cubed. 768 divided by 12 is 64, and then to finish off to find R, we just need to cube root both sides, and we get R is 4. Now we can go back and work out A using equation 1, as it is simpler. So 4A equals 12, A equals 3. So we have the two parameters of our geometric sequence. These two numbers define our geometric sequence. So that means we can now write down the general term, the nth term, which is what the question is after, as A, which is 3, times by R, which is 4, to the n minus 1. Now we need to be very careful here. As much as we go on about simplifying expressions in final answers in maths, we do need to be careful not to simplify when we're not actually supposed to or not able to. So there's a very common simplification to this which isn't actually valid, and that's to go, okay, we've got 3 times 4 to the n minus 1, so that would be 12 to the n minus 1. Please do not do this. This is because the 3 is not raised to the power of n minus 1, therefore cannot be collected together with the 4. What we actually have here is 3 times 4 times 4 times 4, and then this goes on n minus 1 times, but we only have 1 3. Okay, whereas the 12 to the n minus 1, that suggests that we've got 3 times 4 times 3 times 4, so this is the 12 over and over again, meaning we have multiple 3's appearing in this product, which just is not true. So make sure that you leave your answer in this form. If you don't want to write the times sign, you can always use brackets, so 3 times 4 to the n minus 1 is a perfectly acceptable answer. Just do not times them. Okay, so in this question we are given that the first 3 terms of a geometric sequence are these expressions in x, and we need to work out the possible values of x. Always make note of how many answers you're expecting to have, so here definitely more than one. Now when we encountered a question like this in arithmetic, we had to subtract the first term from the second term and then equate that to this difference between the second and third terms, because we knew we were looking for a common difference. Because we know this series, or this sequence, is geometric, then we know we need the common ratios to be equal, and that requires division. So the equation we can set up is 4x minus 1, so that's the second term, divided by x plus 1. That must be equal to 10x plus 5 divided by 4x minus 1. So the common ratio that takes us from the first to the second term must be equal to the ratio that takes us from the second to the third term. Now that we've set up the equation, we can rearrange it. The nicest thing to do here would be to multiply up by the denominators. So that will give us 4x minus 1 squared is equal to 10x plus 5 multiplied by x plus 1. So let's expand this. We'll get 16x squared minus 8x plus 1 is equal to 10x squared plus 15x plus 5. So we've got a quadratic equation. This ties in nicely with our multiple values of x. If we move everything over onto one side, so we'll take the 10x, we'll get 6x squared. Take the 15, we'll get minus 23x. Take the 5, we'll get minus 4. Okay, so let's see if this is going to factorize. So we're going to add to make and times to make, so adding to make minus 23, multiplying to make minus 24. Let's see what works here. We've got minus 24 and 1. So I'm going to split the middle term. 6x squared minus 24x plus x minus 4. Split it down the middle and factorize each half. 6x, open brackets, x minus 4 plus 1 lot of x minus 4. So that gives us a 6x plus 1 and an x minus 4. So we have two possible answers here then. Minus 1 over 6, or x equals 4. And we are not required to do anything more. We've worked out our value of x. We are done. Okay, so now we need to move on to look at series. So this is where we add all the terms of the sequence up. It becomes a series. And we are going to look at the nth term of geometric. And by doing that, we're actually going to go through the proof as well. So what I'm about to show you not only shows you where this formula comes from, but it is also a proof that you may be expected to reproduce in the exam. So make sure you learn how it works. We're going to denote the sum to n terms in the same way that we did with arithmetic. So it's still going to be Sn. And we're going to start by writing out a few terms like we did with arithmetic. So a plus AR plus AR squared, dot, 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 to denote that it carries on in the same way. We know that our last term is going to be AR to the n minus 1. So let's have AR to the n minus 3 plus AR to the n minus 2. Just remember that you are ending on AR to the n minus 1, not AR to the n. It's always one less because we start with R to the 0. Now in arithmetic, we then wrote our sequence out backwards so that we could add them together and get the same term over and over again. That's not going to work here, but we do have another trick where we multiply through the whole sum with R. So what that has the effect of is bumping up every term to look like the term ahead of it. So here we start with AR, dot, dot, dot. And this one would bump up to be n minus 2. This one would be bumping up to n minus 1. And then we would get AR to the n at the end here. Now what we can do, we normally add at this point in the arithmetic one. Here we are going to subtract, because if we subtract we are going to be cancelling out the diagonal terms from the way that I've written it. So if I just subtract in the order that I see it, then I will get Sn minus Rsn on the left hand side. On the right hand side we're going to get an A, because that doesn't cancel out with anything in the second expression. And then AR and AR will cancel, AR squared will cancel, the AR cubed will cancel with something we haven't written. This term will cancel with the term before here, and all of these will also cancel in that subtraction, leaving us with, well, nothing from the first line minus, well, apart from the A, minus the AR to the n. Now our aim is to get an expression for Sn, so we need to get Sn as the subject. If we look on the left hand side here, what we need to do is factorise Sn out. So we get Sn times 1 minus r. We can also factorise a out on this side to make it look a bit nicer. And then to finish off, we just divide by the 1 minus r. And that is our Sn formula. Let's pop that up in the corner. Oh, wrong one. There we go. Okay, there is another way of writing this just to be aware of, and which one you use will depend on your value of r in the question. So this version of the formula is quite nice if r is less than 1, because it means you'll get positive terms on the top and the bottom. What we can do is basically multiply the numerator and the denominator by -1, which has the effect of flipping around the order of this, the 1 and the r to the n and the 1 and the r. So we could write it as a times r to the n minus 1 over r minus 1. This is better if your r is larger than 1, again giving you positive values on the top and the bottom. It doesn't matter if you use either one for any question, you just might have to do it more negatives if you choose one that doesn't work as well. Okay, before we move on to some questions, we need to deal with this sum to infinity idea. Now, sum to infinity only works for what we call convergent series. A convergent series is a series where every term that you add on gets smaller and smaller, which means that your sum converges, it tends to a particular value. Now, in order for each term to get smaller and smaller, we have to put the restriction that r is a number whose size is less than 1. So, for example, if we multiply by a half every time, then our numbers would definitely be getting smaller. The same would be happening if we multiply by -1/2. They would just bounce around between being positive and negative. So we could write this as r has to be between -1 and 1. A slightly more compact way of writing this is to use the modulus sign. So this says that the size of r, mod r, these lines either side, has to be less than 1. So this is the only time that we can use the sum to infinity formula, because if the series is not convergent, i.e. divergent, then if you try to add up the terms to infinity, then you will just get a very large number that continuously grows. You cannot work it out as a single value. So in order to work out what the S infinity formula is, we need to have a look at the Sn formula again. And because we're working with numbers smaller than 1 as r, we're going to use the version that we first came up with, which is the 1 minus r to the n over 1 minus r. Now, if mod r is less than 1, then as we take n to infinity, the value of r to the n is going to get smaller and smaller. So let's take our example of, I don't know, a third. If I keep raising a third to higher and higher powers, I would get a third, a ninth, a third, a ninth, and then 1 over 81, etc. The point is it's getting smaller and smaller, so we can say that it tends to 0. Now if Rn is tending to 0, then we can look at our Sn, and this term here is the only term that has an n in it. So Sn will tend to A times 1 minus 0 over 1 minus R, because that R to the n term is disappearing as n gets very large. So that means we can write that S infinity, so this is how we denote sum to infinity, is A over 1 minus R. Okay, so we'll just add that to our list of formula in the corner. Now that we have all the formula that we would need, let's have a go at a couple of questions. Okay, so what have we got here? The sum of the first 4 terms of a geometric series is 369, and the common ratio is 5 over 4. Find the first term of the series given your answer as an exact fraction. Okay, the sum of the first 4 terms. That can be written as S4. The formula for that is up in the corner. We'll use this formula, but note that we do have the common ratio 5 over 4. Which version shall we use? Well, the common ratio is over 1, so I'm going to use the one that has the R to the n first. So A is the thing we're trying to find, we still don't know it. And then it's going to be 5 over 4 raised to the power of 4. So this, careful here, in the nth terms, we use n minus 1. In the sum to n terms for geometric only, we just use n. So that's going to be to the 4 minus 1 over 5 over 4 minus 1, which is a quarter. And this therefore has to be equal to 369. So we can sort this out a little bit. Okay, so doing a bit of rearranging, we get 369 over 256a is equal to a quarter times 369. Solving that, 369 is going to cancel. A quarter times 256, that tells us that a is 64. Then we are required to find the 7th term, so that's u7. So that will be 64 multiplied by our common ratio 5 over 4. Now this time we do take away 1, so that's the power of 6. And we're writing this as an exact fraction, so that comes out as 15,625 over 64. Okay, part C. Find the least value of n for which the sum of the first n terms of the series, that should be an is, greater than 50,000. So we're looking for when Sn is greater than 50,000. Now we have our A and our R, so we can put Sn in, put that into our formula. We would have 64 times 5 over 4 to the power of n minus 1 over a quarter, and that needs to be larger than 50,000. Now what we need to do is rearrange this to get the term with n in it on its own on one side of the equation. So if we do that, we get 5 over 4 raised to the n has to be larger than 3,141 over 16. And this is where our log work comes in. Now we've got a couple of options here. You can go for log base 5 over 4 of the fraction on the other side. What I think is slightly safer, plus I've seen many questions that actually require you to do it this way because it will be a show that, and you have to show it arrives at a particular equation which uses this form. And that is to either apply log base 10 to both sides or natural log to both sides. Generally speaking, I've seen questions that use log base 10 more often. I tend to prefer using natural log just because there's a button on my calculator for it and I don't have to press shift in order to use it. I'll use log base 10 in this question. It makes no difference which base you use, just because it is more common in the exam questions. So the way we do that then is to write log on each side first to show what we are doing. So log of this side is larger than log of this side. And then what we're able to do is bring the n down using our log law, one of our log laws, giving us log base 10 of 5/4 is larger than log base 10 of 3141/16. Okay, and then it just requires dividing by the log 5/4. This is where you need to be careful and think about it, because if the number inside the log here was a number less than 1, then we would be dividing by a negative. Because if you remember the log graph, which looks like this, goes through 1 on the x-axis. If you put in any number between 0 and 1, you go down, meaning you get a negative output. So you will get a change of inequality sign when you do that, so please be careful. For us here, our value is greater than 1, so it makes no difference, so it still stays as a greater than. Now if you divide, so log of all of that, divided by log of 5/4, which I'm not going to write down because it takes too long, we get 23.66, and there's some more numbers. So we want the least value of n, so if n has to be larger than 23.6, then the least value of n is 24. There we go. Okay, question 4. We've got a couple more questions to go in this video. We are given the sum Sn of the first n terms is given by this, 2 to the n minus 1. Find the first term and the fourth term of the series. Okay, what we are not going to do is try and compare 2 to the n minus 1 to the general formula. We can do this in a much easier way. Note that if we want the first term, that is equal to the sum to the first term. So to get a, we just need to evaluate S1. So that would be 2 to the 1 minus 1, which is just 1. The fourth term, okay, so what we can do to work out that is take, so U4, is we can take the sum to the first 4 terms, and then we can subtract the sum to the first 3 terms, and that will give us the term that we added on to get the sum of the first 4. So S4, that would be 2 to the 4 minus 1, minus 2 to the 3 minus 1. So 2 to the 4 is 16, so that would be 15, minus 2 to the 3 is 8, 8 minus 1 is 7, 15 minus 7 is 8. So we've got A and we've got our U4. Part B, find an expression for the nth term. Okay, in order to do that we need A and R. We've already got A, so that leaves us to find R. We kind of need to find the well, we could actually take our U4 and U1, work that way, because U4 is equal to AR cubed. So if we took U4 and divided it by U1, which is A, we would just get the R cubed. That means that we have got 8 divided by 1 being R cubed, which leads us quite nicely to R is 2, which means we can write down the UN is 1 times 2 to the n minus 1, and that 1 does absolutely nothing, so we can drop it and just write 2 to the n minus 1. Okay, the question turned out to be fairly easy. Right, last question of the video, question 5. Okay, so this looks like a question in context, or what we might call a modelling question. When a ball is dropped onto a horizontal floor, it bounces such that it reaches a maximum height of 80% of the height from which it was dropped. Find the maximum height the ball reaches after its 4th bounce, when it's initially dropped from 2 meters above the floor. Okay, so let's think about this. If a ball is initially dropped 2 meters, it then bounces at 80%. So the first bounce would go to 2 times 0.8. The second bounce would be a bit lower. It would go as high as 2 times 0.8 squared. and it will carry on this way. So note here, we need to be very careful, because where we might think this is n equals 1, n equals 2, n equals 3, therefore it's n equals 4 for the fourth bounce. If we put n equals 4 into our UN formula, we would actually work out AR cubed. But here, for the fourth bounce, we'd actually want 0.8 to the 4, because really we'd maybe count our first height as being 2. So fourth bounce would be 2 times 0.8 to the 4, because it's gone through 4 bounces, and we would have times by 0.8 4 times by the time we get to just after the fourth bounce. So let's work out what that is. Okay, so that gives us 512 over 625, which is 0.8192 meters. Okay, part B. Show that when the ball is dropped from a height of h, so we're generalizing here, above the floor, it travels a total distance of 9h meters before coming to rest. A fairly tricky question, this one. So let's think about total height. So first of all, we're going to drop from the place that the ball's let go to hitting the floor. So that's going to be h. And then after the first bounce, we're going to go up to the next maximum height, which will be 0.8h. And then we're going to come down again before we enter the second bounce. So actually there's going to be 2 lots of 0.8h. And then on the second bounce, again, we're going to have the same thing. It's going to go up and then back down again. So we're going to get 2 lots of the maximum height after the second bounce, which will be 0.8 squared. And this pattern will continue. So what we've got here then is h, which is a different, this is not the same as the other terms in this series. This is going to be kept separate. So h times 2 lots of, and then we do have something that resembles a geometric series in here, and that's going to continue on. I should have put a plus ... back here, really. Okay, so let's just think about this bit here. This is a geometric sequence. It has a first term of 0.8 and a common ratio, sorry, it's a first term of 0.8h and a common ratio of 0.8. That means if we wrote this out again, so total, we would want h plus 2 lots of, now we don't know when this is going to stop, but when it does come to rest, it's no longer going to be bouncing. So we're going to basically be taking this to infinity. So actually we want 2 lots of s infinity. So that's going to be h plus 2 times sum to infinity formula. So that's 0.8h over 1 minus r, which is 0.2. So that will be h plus 2 times, okay, 0.8 divided by 0.2 is 4. So we can pop that in. You can see this is working out quite nicely. So that gives us h plus 8h, which is 9h meters as required. Quite a tricky question to think about that one. You have to be very careful with your starting height, and to notice that we are multiplying by 2 for going up and coming down after every bounce. Okay, so that brings us to the end of the video on geometric sequences and series. The next video we'll be practicing a bunch of questions like we did with the arithmetic, and then after that we will go on to things like recurrence relations and sigma notation. So I hope you found the video helpful, and if you did, please don't forget to hit the thumbs up button. Subscribe if you'd like to see more, and I look forward to seeing you in the next one. Bye.